Alright class, this is a little video about how to figure out the empirical formula of a compound from experimental data. And this is example 612 in the book on page 189, but I just wanted you to make sure you understand how he did what he did. So if we take the information we've got here, let's start with this. A sample of brown colored gas is decomposed into 2.34 grams of nitrogen and 5.34 grams of oxygen. So what we know there is we know We know the products of this reaction are N2, because nitrogen is a homonuclear diatomic, and O2, right? Well, if we know that that's the products, we know that the reactants had to be an N and an O. What we don't know is what the subscripts are here. And that's why in the book he uses an X and a Y for just things we don't know, just like in any other algebra problem. Now, so the first thing we got to see here is we got grams and grams. And again, the first thing you should say is, whoa, grams. I can't do anything with grams. So let's figure out just how we've done this before. How do we turn 2.34 grams of N2, put it over 1, and how do we turn it into moles? Well, we want to get rid of grams, so we're going to put grams down here, N2, and moles of N2 up here. And we know this coefficient we're going to figure out here. We know this is going to be 1 mole. And the atomic mass of nitrogen is 14, so 2 nitrogens would be 28.0 grams of nitrogen is 1 mole. It's the same thing, 1 mole. And now again, what we can do here is cancel out the grams of nitrogen, that leaves us moles, and if we multiply we divide 2.34 divided by 28.0, we come up with an answer of 0.0836 moles of nitrogen. Good, excellent. And we'll write significant figures because we got 3 significant figures here, 3 here. We have 3 significant figures here, 1, 2, 3. Excellent. Now we want to do the same thing with oxygen. Okay, so we have 5.34 grams of O2, because again, oxygen is a homonuclear diatomic. We want to get rid of grams, so we're going to put grams of O2 down here. I'm going to put moles of O2 up here. It's going to be 1. Oxygen, of course, is 16.0 grams in terms of 1, so we got to do 32.0 because we got 2 atoms. So now we can do this math too. 5.0, we cancel out our grams, 5.34 divided by 32 will give us an answer of 0.167 moles of O2. Excellent. Well, what we can't do, we can't write 0.0836 and 0.167 here. Because if you remember, John Dalton told us we got to do whole number coefficients. And that's where the next step of the math comes in. So once again, we converted from grams to moles of nitrogen, from grams to moles of oxygen, but now we've got to figure out a way to turn this into a whole number integer. Turn the page here because I'm looking at that too. So the way we do this is to simply divide both of these numbers by the smallest number. Well, that would be 0.0836, right? And this number divided by this number would equal 1. And if we divide this number by 0.836, it's going to give us well, what's the math there? It's gonna, if we do that, it's going to be pretty close to 2. I don't know exactly what the number is going to be, but if you just divide that by that, it's going to be really close to 2. So what that tells us is that we have 1 mole of N2 and 2 moles of O2, right? And now we can figure out what the N and the O must be. We got 2 atoms here, right? So that means there's going to be 2 here. We know there's 4 here, so this has to be 4, right? But again, this if we want empirical, we can reduce this both by 2, right? So 2 divided by 2 is 1, and 4 divided by 2 is 2. So this would be the empirical formula. I don't know if that helps. I'll be glad to ask questions if you post them or send them to me, and we'll see what happens.